This video will be based on a continuation of energetics and stabilization of small rings. So now in this video we will talk about chair and flip chair conformations and how that relates to puckering. Now in our previous video we mentioned that there is Bayer strain and that there is also torsional strain when we are referring to rings. And that puckering actually is able to help reduce that strain and help with stability. Well, now we are going to talk about steric strain. And steric strain will actually be reduced once again by puckering. So we'll be talking about that here shortly. And now I want to talk about chair conformations. And these are directly related to cyclohexane rings. And that's what this video is going to be about. And it's all going to be in reference to the cyclohexane ring, unlike in the other videos where we mentioned cyclopropane, cyclobutane, and cyclopentane. So with this chair conformation, we have one of two angles that we will be looking at. One of them being axial, and an axial just means that we have a bond that's pointing straight up and straight down. And then we have equatorial, and equatorial simply implies that we have a bond that's moving to the side, such as that of like an equator, and that helps people memorize that. But EE just is going to simply represent that that these are going to be equatorial, while A is axial. So now I want to talk about some examples where we have a chair and flip chair conformation. And so this will be represented as a chair, and over on this side we will have a flip chair. And when we're going through this flip chair process, I think it's convenient to visualize these carbon bonds, because that'll help us trace how things are flipping. And what I mean by that is, for example, when we go from this chair conformation to a flip chair, we are actually rotating through space all of these carbons, and it's really like a domino effect where everything kind of gets shifted and moved over from this position in space to, for example, this position in space. And when I'm saying that these carbons are moving, I'm not suggesting that bonds are being broken or anything like that. What I'm simply stating is that these carbons are just moving from one dimension in space to the other dimension in space. And another thing that I want to point out is that whenever you go from a chair to a flip chair conformation, everything that was once axial becomes equatorial, and everything that was equatorial becomes axial. And we will show that with this methyl group. And in this case we have a methyl group that's axial, and it flips or shifts over to this side of the ring, and we can see that right here. And we can also see that it is equatorial now. So that was a flip. Now we can keep we can add some more examples to this. For example, I can add an alcohol or a hydroxyl group over here, and this is axial. But if I flip it and move it over here, I will end up with my alcohol group over here in the equatorial position, because remember, we were axial before. And we can just keep adding stuff to this. I mean, I could say that there's a deuterium right here in the equatorial position, but then it flips over here, and so now I have a deuterium in the axial position with the flip chair. And so I think that that helps visualize what's going on. And by the way, if we're going vice versa, if we're going flip chair to chair, we just basically move in the opposite direction, and we show our domino effect moving backwards essentially from what we demonstrated before. And so that's how we represent chair to flip chair conformations, and how things that are axial become equatorial and equatorial become axial. But another point I want to mention is that when we are looking at these conformations, we are typically looking at them in equilibrium. So I'll just draw some equilibrium arrows right here. And what I mean by equilibrium, if we go back to Gen Chem, remember if we have a K value, for example, and K just represents that we are in equilibrium. But if I have a K value that is greater than 1, then I am suggesting that my products are favored. And if I have a K value that is less than 1, I am suggesting that my reactants are favored. If my K value equals 1, then neither the products or reactants are favored. And remember, our K values are determined by this equation where we have a concentration of products over a concentration of reactants. And so it makes sense that, if we have a K value that is greater than 1, well that should imply that we have more products than we have reactants. And that just makes sense mathematically, because we would need a higher amount in our numerator than we do in our denominator to have a value that is greater than 1. And conversely to that, if we were suggesting that we had a K value that was less than 1, well, now we need the opposite to be true. We need more reactants than we have in our products, and as a result, we will demonstrate a K value that is less than 1. So I just wanted to give that quick review on equilibrium. Now let's apply some of this information to an example where we demonstrate steric strain, and that was mentioned at the beginning of the video, and now we can show an example of that. So if we have a methyl group, for example, that is in the axial position, this is actually going to take up a lot of space, and this space is actually determined mostly by atomic radius, or atomic radii, depending on if we're working with multiple atoms or not. And so this is actually going to take up a lot of space right here. And by the way, we are going to suggest that we have hydrogens attached to all of these bonds, because if there's nothing attached to these bonds, it is implied that we are working with a methyl group. And so, for clarification, I want to show this. And so, as you can see, this methyl group in the axial position is now interacting with all of this, and it's also interacting over here too. So there's a lot of strain, and for that reason, really, I mean, we are always going to want our substituents to be pointing in the equatorial position, to avoid that steric strain, and that's why it's always going to be more favorable energetically as well. And as you can see, as we went through this this chair to flip chair conformation, we actually demonstrated that we moved from this carbon to this carbon, as mentioned in our previous example, and shown in our previous example. So now we are over here, but we are also in an equatorial position. And so it's still going to occupy the same amount of space, but now it's going to have a lot more freedom to do so. And that's just reinforcing what I said earlier in reference to substituents wanting to be in that equatorial position relative to the axial position. And so now let's continue on with this example and demonstrate this in equilibrium, and let's apply this to a new circumstance. So if we are in equilibrium, that might suggest that we are going to have more products than we are reactants. Because remember, we want things to be, or we want substituents that take up a lot of space to be in the equatorial position. And so if this is going to be energetically more favorable, we should ultimately have more product of this. And we'll say 95% product of the equatorial position, and we'll say 5% product of that in the axial position. And by the way, these examples and these numbers are just our guesses as to what the percentages would actually be, but they should be relatively close. And so now, if we are saying that we have 95% this product and 5% of the chair product, and let me just write that these are our products. And we'll just call them concentrations, and these will be our reactants. We will now show a K value that looks something like this, where we have our products over our reactants. But remember, our products are going to be 95% relative to the 5% of the reactants. So we are going to have a lot of this and a small amount of this. And so now we are going to end up with a K value that is actually a lot larger than 1. And when we have that, we can say that our products are going to be favored. So now let's add one more example to this so we can tie it all into one big picture. And we can do that by showing this now on a Gibbs free energy diagram. So let's see here. We can show our energy diagram like this. And this is going to be our energy, and this is just going to be a reaction coordinate. And so we will end up with something that looks like this. And by the way, I'll go over this as soon as I'm finished drawing it. And so this is going to be our first transition state, which is going to represent a 1/2 chair. This down here is going to represent a twist boat. Right up here we have a boat conformation. Another twist boat. And up here we have another transition state of a 1/2 chair. And over here is going to be our flip chair. And on this side, remember, we just simply had our chair conformation. And by the way, these are our products. And over here are our reactants. So now you can see that we're actually moving from this level down to this level. And that's also going to imply that we have a negative delta G standard. So I can just show that right here. So negative delta, actually this is a delta sign, negative delta G standard. And that's just showing that we are moving in a spontaneous reaction, and that our products are going to be favorable over our reactants. And we've demonstrated that not only energetically now, but we've also demonstrated that previously by suggesting that we are going to have more products as a result, and less products. And that just basically all ties into the K value being greater than 1. And so that is that's our continuation on energetics and stabilization of small rings. Hopefully this video was helpful and you are now able to tie in some of these concepts.